All right, so the topic today is energy from chemicals. It's a very easy, short topic. And the idea here is that chemical reactions, they not only involve rearrangement of particles, because we have seen that when things react, they break their bonds, they make new bonds. The atoms or the particles are rearranged to some extent. But it's also that there is also energy related to it, some energy change. And the idea here is that how we can use that or understand that to our advantage. So first of all, you have to understand what energy is. So energy is the ability in a body to do work. Okay, so you can use it to do anything. And we have so many different forms of energy. We have heat energy, which is the most common form of energy. And then we have electrical energy. We also have sound energy and all that, that is related to chemical reactions. So what exactly is a chemical reaction? You rearrange the particles using or spending some energy. And there is always bond making. And there is always usually some bond breaking. Turns out, if you have things joined together already, you want to split them apart, you want to separate them, you have to supply enough energy to break that. So this means that you have to supply energy. You have to give energy to those things. Why? Because when you give energy to those things, so for example, you have two things that are joined together through this bond, you give them energy, so these start to move, and this also starts to move. And so eventually, once they have enough energy, they can break this bond that they have and go their separate ways. So you have to supply energy for bonds to be broken. But once you have them separated from each other and they have some high energy, you want them to combine together. When they do that, they're going to collide with each other and they're going to release energy. Okay, so in bond breaking, there's going to be some absorption of energy. They absorb energy. You have to supply that energy. But when they make new bonds, they're going to release that extra energy that they have. Whenever something releases energy, we say that this is exothermic. Why thermic? Because heat is the usual form. And exo means exiting. So heat is exiting these things. So they had that energy in them, and now it is exiting them. Similarly, when you break bonds, that is endothermic. Endo means heat is entering, and heat is again the dominant form of energy that we have in these reactions. So there you go. In any reaction, you have bond making and bond breaking usually. There are some forms where you don't have to make new bonds or where you don't have to break any bonds. That does happen. But bond making will always release energy and bond breaking will always absorb or accept or take energy, and you have to supply that with them. We always say that when you give energy to something, the energy rises. So we show that with a positive sign, that energy is rising. And when you take energy from it, there's going to be a decrease, which means we show it as a decrease in energy through a negative sign. It is positive if it is rising, and it is negative if it is decreasing. Okay. So a decrease is when energy is given out, and that means it's exothermic. Now, that is something that some students struggle with sometimes. They're like, if energy is exiting, should it be positive that, oh, temperature is going to rise? But the thing is, we're not talking about the environment. We're not talking about what happens outside those things. We're talking about these particles. These particles, before the reaction, they had high energy in them. And after bond making, they have lost that energy. So where that energy goes is irrelevant to those particles. They've just given it out. That is why bond making is negative. They have lost that energy. And bond breaking is when they take energy. Where do they take it from? And what are these particles? So for that, we introduce the idea of environment or surroundings and the system. So system is what all those particles that are taking part in a reaction. That is what system is. These are the particles taking part in the reaction. And surrounding is everything else. So for example, you take some calcium and you put it in a beaker. So you have calcium pieces and you put them in a beaker. And that beaker has HCl in it. So you have taken some calcium. So you have calcium blocks and you put them in HCl. They're going to collide. They're going to react. Now, and you obviously want to measure the temperature. So you put a thermometer in there. So there's a thermometer. You also don't want the energy to be lost. So there's a lid there. Okay. So all of that is there. What is the system here and what are the surroundings here? Tell me, take a guess. What's the system? What's the surroundings? Remember, system is what takes part in the reaction. And surroundings is what is not taking part in the reaction, anything outside. Okay? Yeah, so what do you think? What is taking part in the reaction and what is not? So it is the reaction between calcium and HCl particles, right? They're doing something there. Calcium is replacing hydrogen gas, and so the reaction is happening. So the system here is just this thing. This is what system is. The calcium particles and the HCl particles. Because HCl is liquid, HCl is dissolved in water, there are water particles there. But that is not part of the system. This lid is outside of these calcium atoms and HCl molecules. This is not part of the system. Thermometer is not part of the system. Beaker is not part of the system. The person doing the experiment is not part of the system. They're all surroundings. System is only the things that are taking part, which means that these particles, calcium particles and HCl molecules, they had some energy in them. When they react, they're going to give that energy out, which means the system will give energy to the surroundings. So system had some energy. It has given it to the surroundings. What will happen to the energy of the system? So it had some energy. Let me put energy here. So it had energy at this level. And after the reaction, it gave that away. So now it is at this level. So overall, you can see that energy has gone down, right? Similarly, there might be a reaction like, I'll give you an example of calcium carbonate. You heat it, so you're giving it some heat, you heat it, and now it has broken down and converted to calcium oxide and carbon dioxide. Because you are the one who supplied energy here. So the system had low energy initially, but at the end, the system now has high energy. So this is energy. So the overall, the energy has gone up. Here, energy has gone down. Here, energy has gone up overall. This thing, where energy goes down overall, where has the energy gone? Energy has gone to the surroundings. This we call exothermic. And when this energy has gone up, where has the energy come from? It is coming from the heat that you gave. What are you? Your surroundings. So when surroundings provide energy to the system is what takes part in the reaction, okay? When the surroundings, the person doing the experiment, the Bunsen burner that you have, the fuel that you're burning, whatever you have, when that gives energy to these particles taking part in the reaction, we say this is endothermic. So endo is whenever you give energy, and by you, I mean the surroundings. And exo is whenever those particles, the system, they give energy. So let me give an example. Let's suppose you have sunlight falling on a leaf, and that leaf is doing photosynthesis. What is the system here? Tell me. So in photosynthesis, what happens is you take carbon dioxide from the air and water from that is absorbed by the roots, usually, and they react together to form glucose. So the system here, what would that be? There's obviously chloroplast there. There's the plant. There's the air around it. There's probably a gardener somewhere around there somewhere. There's the sunlight coming in. What is the system? No, system is not thermometer or anything. As I told you, system is what takes part in the reaction. So it is the carbon dioxide molecules and the water molecules. That's it. Those are the system. There is chloroplast there, sure. That is also the system. But the plant itself, the gardener, the air, the sun, they are not system. They're surroundings. Would this be endo or would this be exo? Now you know that photosynthesis will not happen without light, sunlight. So it is taking energy from the surroundings. That is why this is endothermic process. It takes energy from outside the system. Those particles of carbon dioxide and water, they are not providing the energy. It is the sunlight that's giving that energy. But you take another example. You eat something. Your body is going to do respiration, take energy out of that thing. That is exothermic. Why? Because food that you had, it had glucose in it, and that glucose had energy stored in it. And when you did respiration, that energy was given out. So that is exothermic. So we can classify reactions as exothermic and endothermic, and that simply means that the energy of the system, the things that are taking part in that reaction, it will either rise or it will either decrease. So for example, photosynthesis is an example of endothermic reaction. Decomposition is also something that we break things down by giving them heat. An example is written right in front of you over here. That calcium carbonate, we heated it, it gave calcium oxide. So that is decomposition. That is also an endothermic process. These are both endothermic processes because you're giving energy. Exothermic processes may be combustion. You take some fuel, you burn it. That fuel has energy in it. You're driving a car, you put petrol in there, and now you're driving it. Where are you getting the energy from? From the petrol. Where did petrol get its energy from? It had in it. It had it in the molecules of hydrocarbons or these organic compounds that it had in it. So it's giving that energy out, and that is how you're driving a car. That is how you might cook food using methane or petroleum gases. That is how you will. So respiration is also exothermic because the food that you had, it had energy stored in it. So you were able to extract that energy out. Obviously, you have a whole system in your body that works so you can take the energy out of the food. You need a specific equipment to do that. If that equipment breaks down or there's a problem, so that is going to have some detrimental effects. So when the system is required, sure, but system is getting the energy here, not providing the energy here when you're doing respiration. Similarly, you have these exothermic reactions that are opposite of, so photosynthesis and respiration, you can say that they're opposites, kind of. Respiration, photosynthesis is where they absorb energy from the sunlight, and respiration when you take that energy out. So that's exothermic. So in general, these reactions are exothermic and endothermic. But in the beginning, I said bond making is exothermic, bond breaking is endothermic. How does that relate to these reactions? Because if I take any of these reactions, what happens is that, for example, in combustion, let's suppose I have methane, I burn it. In presence of oxygen, we're going to get carbon dioxide and water. At this point, you don't need to know how to make this equation. So I balance this out. Yeah. What's happening? If I were to draw this methane had this structure, and this oxygen had this structure. Two oxygen molecules, okay? And now they have this structure, carbon dioxide, and two water molecules. If you look at this, these are the bonds that were there. This bond is there now. And how many bonds of these? So you have 4 bonds between carbon and hydrogen, and you have 2 bonds between oxygen, 2 double bonds between oxygen, right? So one in this molecule, one in this molecule. These are the bonds that you break. And on the other side, you have carbon making a bond with oxygen, and there are two of them because in one molecule of carbon dioxide, there's one with this oxygen, one with this oxygen. You also have 4 bonds between hydrogen and oxygen, right? These. And these are the bonds that are made. Now, how do I know that this reaction is indeed exothermic or endothermic? I can calculate the energy of these bonds. What? Bond energy? Yeah, that's a term. What is bond energy? Bond energy is the energy required to break a bond. So every bond has some energy that it's storing in it. So if you supply that energy, it breaks down. And you can Google it out. So you can check that, all right, what is the bond energy of carbon and hydrogen? So if you look at it, so I just Googled it. So bond energy, or sometimes we also call it bond enthalpy. So for its CH, that is, so there are 4 of these 4 CH bonds, and that is 413. Okay, so for oxygen, so let's look at it for oxygen. So if you Google it, oxygen bond, the double bond of oxygen has the energy of 494. So there are 2 of them. So 494 times 2. Similarly, these bonds, the ones that you make, they also have some energy. So carbon double bond with oxygen, it has the energy of 799. Okay, so 799 for this one. So there are 2 of them. Similarly, hydrogen and oxygen bonds. So I can just Google that as well. So hydrogen and oxygen bond, and that is 464. Okay, so let's try to calculate this. In the numerator over here, over here, we have the energy that is supplied. Okay, so if I were to calculate this, so this is 4 times 413 plus 2 times 494. It has calculated it, that 2640 total joules or kilojoules that are being supplied so you can break the bonds. Notice that these are the bonds that we are breaking. So to do this reaction, you have to break these bonds, and you have to supply 2640 kilojoules of energy. Now let me see over here. So I have 2 times 799 plus 4 times 464. And how much is that? That is 3,454 kilojoules of energy that is being released. So this is the energy that I had to provide, which means it was positive. And this is the energy that was released. So let me try to add these things. So I had 2640 that was given, and I had 3454 that is released. So how much is that? Let's see. So we have 2640 minus 3454, and that comes out to be 814 negative. So it is minus 814 kilojoules. What does that mean? What does that tell me? Number one, it tells me that if you do this reaction, if you burn methane in oxygen, getting carbon dioxide and water, for 1 mole of methane, you're going to get 814 kilojoules. So every 1 mole that I burn, this is the energy change. Not just that, this negative sign, that tells me this is the energy released, which means that the energy released here is more than the energy that was absorbed. So overall, this reaction is exothermic. And that is why methane is such a good fuel. We use it for cooking all the time. It provides really good energy per molecule. And it's really convenient to do it. It's pretty safe otherwise, but when you burn it, it's pretty useful. So how do I classify a reaction as exothermic or endothermic? So I can simply say now that if you want to see what reaction is exothermic and what reaction is endothermic, calculate all the bond energies. So take the bond energies of the bonds that you break, and take the bond energies of the bonds that you break. The bonds broken, they will have a positive energy. So energy of bonds broken, they will have a positive energy. Positive means you're going to supply it. And energy of the bonds that you make, that is going to be released. And that is going to be negative because you're going to release that getting out of the system. So that is equal to what we call delta H or enthalpy. Enthalpy is the energy of a reaction, the overall change in energy, the starting point and the ending point. This thing that I just showed you, this thing, this arrow, this arrow. So this thing now has a name. This is delta H. So as you can see over here, the energy at the starting is low, energy at the end is high. So overall energy has been taken in by the system, which means that energy of bonds that you broke was higher and energy of the bonds that you made was lower, so that overall energy is absorbed. Over here, energy of bonds that you make was higher, energy of bonds broken was lower, so that is why it is negative. Overall energy released. So overall, there's a release and there is an absorption. Energy absorbed and overall energy released. So how is a reaction exothermic? When overall energy is released. Why does that happen? Because the energy of bonds broken is less. Energy of bonds made is more. Similarly, why is a reaction endothermic? It is endothermic because overall energy is absorbed. Why is that so? Because energy of bonds broken is high and the energy of bonds made is less. All of it, of course, depends on this idea that bond making is exothermic and bond breaking is endothermic. Okay, to break a bond, you have to supply energy, and to make a bond, energy is released. All right, so that's it. But here's the thing. You cannot just start a reaction right away. You need some starting investment. That investment of energy that you have to do every single time you start a reaction, we call that activation energy. Activation energy is called EA, is the energy required to start a reaction. So energy, in fact, minimum energy required to start a reaction. So why do you need activation energy? Turns out that if I wanted to do this, I had to first break these particles, right? I can't just make carbon break the bond with hydrogen and make a new bond with oxygen. I can't just randomly do that. Here's a hidden part there. When this reaction actually happens, before this can become this has to first break down. So every carbon and every hydrogen is separate and every oxygen is separate. And then this soup of these atoms, they have to combine and make this. So I have to first break these and make these then. This is going to be bond breaking. This is going to be bond making. And this state, this is called transition state. And to get to transition state, you need to first supply energy. So here's how it goes. So we do a reaction. We start at a certain level of energy. And we want to get to a certain level of energy. But we can't just do that right away. We have to first supply energy to these particles. So we give them energy, so the energy rises, up to a certain level where every particle is independent. Every atom is free. And that is when they start making new bonds and get to this level. This first portion, this is where you give energy. Energy increases. So this is positive. And this level is where energy is released. This side is where bonds are broken. This side is where bonds are made. This side is endo, you're supplying energy. This side is exo, you're taking energy out. And the energy that you need for them to reach this transition state, this transition level, that is called EA. activation energy, the energy that you have to supply for every particle to be independent and able to do the reaction. And then from the starting point here to the ending point here, the difference that you actually make, that is delta H. That is the overall change in energy. And you can see over here that it has decreased. So delta H is negative. You can also have it in a different way. You can have a certain level of energy in the beginning and a certain level that you end up, but you can't just randomly get to that right away. You have to first give them energy. So every particle is independent of the other. And then they break together, they make this. And again, this side from here to this transition state, this is the transition state. This side is positive. We call it activation energy. And this side is negative. This is the energy released. Overall, there has been an increase. This delta H is positive because it has increased in energy, and that is negative. Okay. All right. So we have two kinds of reactions. One in which you increase the overall energy. One in which you decrease the overall energy. But in both of them, what's common is that you have to first supply them some energy to get to the transition state where the reaction actually occurs. And that energy is activation energy. And then you have to get to some level by making new bonds. If the energy of bonds made is high, which means the downside is higher and the upside is lower, then it will be exothermic because you'll end up at a, and if the downside is smaller, as in the case of the second diagram here, the downside is smaller and the upside is higher, then that is overall positive energy. We say that energy is overall taken in, the delta H is positive. This is endo, overall. This is exo, overall. Interesting to note here that the shape of this curve doesn't matter. You can have this shape, you can have this thing, you can have this thing. It doesn't matter. The shape of the graph doesn't matter. As long as you start at some point, you end at some point, and you have a transition state. That's all you need. All right. So some reactions that are endothermic are decomposition and photosynthesis. Some reactions that are exothermic are combustion. For example, we burn stuff, wood, fuels, and respiration. These are exothermic processes. So important terms here, delta H, which is enthalpy change. It is the energy of bonds broken. Mine is the energy of bonds made. Activation energy, which is the minimum energy required to start a reaction. Bond energy, which is the energy required to break a bond. So every bond has some energy related to it. Then how do you know whether reactions are endothermic or exothermic? You calculate all the bonds that are broken, and you calculate the energy of all the bonds that are made, and then you subtract the energy. Remember this point. It is the energy that matters. It is not the number of these bonds. You can have so many bonds that you break. You can have so many bonds that you make, but it is the energy that matters. If the energy of bonds that you make is higher, then there will be a higher negative value. Reaction is exothermic. If the energy of bond that you break is higher, there will be a higher positive value. So the reaction is overall endothermic. There are some reactions in which you don't have to break a bond. You just have to make bonds. So that will be overall exothermic. And in MCQs, they usually give you those. So they already give you a transition states. For example, if I give you carbon and 2 oxygen. Now, this shows that I have everything as atom. This is carbon atom. This is oxygen atom. And they're going to make CO2. So there is no bond breaking part. So this is overall exothermic, as you can see, because I'm only making bonds. Similarly, they might give you something like this, where they say, okay, this breaks down to give you this. Then over here, this is positive delta H, because this is a molecule. This has bonds in it, but these are atoms. They don't have any bonds in them. So that means you didn't make any bonds. But if they give you something like CO2 breaking down to give carbon and O2, now this is a molecule. This is atom. This is a molecule. Again, some bonds are broken, some bonds are made. You cannot figure out whether this is positive or negative until you actually calculate the energies. Until you actually see that, all right, the bond between carbon and oxygen is broken, so that is positive. And the bond between this oxygen molecule is made, that is negative. So this is negative, this is positive. You subtract them overall, and that is how you know that overall this reaction might be positive or negative. This reaction, by the way, this example is endothermic, but you cannot know for sure until you take the values and you calculate them. For O levels or IGCSE, you do not need to remember these values. Do not try to memorize these values. Just memorize the method. Just try to understand the method. You calculate the energy of bonds that you break. You calculate the energy of the bonds that you make. Broken minus made is what you need. And why is that? Because bond breaking is always endothermic. You need to supply energy to break bonds, and bond making is always exothermic. You get energy when you break them. Okay, that's it. That is it.